Hello, this is the Chapter 1 lecture that I'd like you to listen to. So this chapter and this unit is very math heavy. So the first unit in our class is going to be pretty much a lot of math. So I'm going to get you through it, so don't worry about that. I will help you as much as I can. One thing we need to know is how we work on the scientific method in science, and you've probably seen this before, so I'm just going to run through it quickly. And you do this actually in medicine as well. You see a patient with particular vital signs, then you might prescribe a medication and see the effect, and then based on that you can adjust the medication or try a new medication. So you're really doing an experiment on the patient when they come in. So generally we have to find out about the patient, or we have to learn about the subject that we're going to try to work on in a scientific experiment. We come up with a diagnosis. In medicine we call it diagnosis, but in science it's called a hypothesis, which is a working theory about what's happening. We do an experiment. So in the hospital, maybe the emergency room, you give a medication to a patient after you've figured out your diagnosis and see what occurs after you give the medication. If that medication doesn't work well, then you might have to modify your diagnosis, or we call it in science a hypothesis, and try again. And that's perfectly natural and normal to do in science as well as in medicine. You might have to change what you think is happening and revisit your hypothesis and change it and start again. And that's fine. Once you have gone through this process, then you might come up with a tentative acceptance of your hypothesis. You know what the diagnosis is and you know what the treatment plan should be. So that's the scientific method in medicine, and we use the same type of method in science. After we get through the tentative hypothesis and we think that's the correct one, if we have lots and lots of data and we've looked at lots and lots of patients, then we can come up with a theory. And in science, if we have a theory that we have never found an exception for, then we can call it a law. In this class, we'll have to get used to units of measurement. And so we're in the SI system, and we'll be using these units often. And we'll also have to use some metric system, and in medicine you'll have to be using an English system. So you're going to have to get used to a combination of these things. So for example, mass is something that we are measuring the amount of matter that we have in a particular thing. And so in SI we measure that in kilograms. Metric is grams. And the difference between these two is that K is 1,000 of these smaller grams. Length is nice because it's just in meters. Volume, a cubic meter, is used in SI, and the metric is a liter. We use seconds for both times, and in SI we use something called Kelvin, which relates to absolute zero. And so we'll be using this when we do gas law calculations, and we'll use Celsius a lot in this class. You will generally be used to Fahrenheit from taking temperatures if you're in the medical field. We will be doing lots of conversions between one and the other of these units and systems, and so we'll have to get comfortable with the way we do that. And so, like I said, the first unit in this class is very math heavy. After that, it changes to more, to a different type of learning. So please don't get discouraged when we're doing the math section. I will get you through it. So mass, as I was saying, is the amount of material you have in an object, and it doesn't change the location. Weight is a different thing. It's how much gravity is pulling on that mass. So it changes depending on the gravity situation that you're in. We have different units for metric conversions, and the large units are shown in large letters, and the small ones are shown in lowercase. So large units are in capitals, and lowercase is in small letters. So mega is a huge value, it's 1,000,000, and kilo is 1,000. So the ones we really need to know in this class are kilo, deci, centi, and milli. So if you can start getting those into your mind, that would be really helpful, because we're going to be doing lots of conversions with those 4 units especially. And so we'll have to know how to go from one to the other, and one large unit is going to be worth a lot of smaller units. So for example, 1 meter has 1,000 millimeters in it. Milli stands for 1,000. And we'll have to get used to these. So it's good for you now. You might want to put these on flashcards and start learning them. So when we're in class, we have some practice problems. So we'll talk about these in class, but just know that we do practice problems in class for extra credit, and we turn those in at the end of the lecture. It helps you guys with your grade, and helps hopefully give you a little incentive to come to class. And so we'll do these in class together. So when we do measurements in the lab, we need to measure them accurately. And we're going to be using something called the meniscus when we have liquid measurements. So this thing right here is called the graduated cylinder. And it's graduated, which means it has little lines. And so we're going to be trying this when we do our first lab in class. And we have to get used to where we're going to measure and where we're going to figure out how much volume we have. So we're going to go to this bottom of this line right here, not to here, but we're going to measure at this line right here, and that's called the meniscus. It's because water has surface tension and it likes to cling to the glass. And so to be accurate, we're going to measure at this level right here, not this level here. So in lab, we're hoping that, and in your careers as well, especially for medical things, we want our measurements to be accurate. We'd also like them to be precise, so that precision and accuracy are 2 different things. Accuracy is how close you are to the actual value, and precision is how close repeated measurements are to each other. So one does not mean the other. We want to be accurate and precise. So if you have all of your measurements really, really close together, that's called being very precise. But you can be precise and not be accurate. Say we wanted to hit this target and get lots of points. We wanted to win the game. We'd want to get right here. Well, we're a pretty good shot because we can get them all together, but we can't get that. We're not close to the actual value. So this is precise, but not accurate. It's not close to the true value. This situation is where you have random measurements. They're all over the place. They're not precise. And they're not really close to the actual value. So these are not precise. They're very random. Let me go back for a second. If we had everything in the center, we had all of them in the center, they would be accurate and precise. So we're going to be using something called significant figures in this class, and it's a way of getting our measurements to be as accurate as we can be. Some of our instruments are going to be, we're going to be able to measure lots and lots of numbers, and some we can only get 1 or 2 numbers out of them. And so when we have to do multiplication, adding, subtracting, multiplying, we cannot get an answer that's more accurate than the machines that we are using. So we're going to use something called significant figures to figure out how to round the math when we're done. So we always round at the very end. So there's rules, so we have to know the rules. Zeros may or may not be significant. In this example, we have a 2, that's a significant figure. The 0 is significant because it's in the middle of numbers. This 2 is significant. I have a decimal, and I have 2 zeros afterwards. So in this example, I have 5 significant figures. These zeros are significant because I have a decimal place right there, and that shows that the machine I'm using can actually read to these places. So it's just like if you jump on the scale in the morning and you see that you're 170.0 pounds, that 0 counts because you may be really wondering if you had lost a half a pound. So 170.5 would matter to you. So this point tells us that we have a machine that can measure way out to this place. So this example has 5 significant figures. So those zeros count. In this example, the zeros don't count because they're showing how small this 2 is. So any zeros to the left of a number do not count. These ones here, I always see one significant figure because I don't see a decimal place anywhere, so I'm not sure how great this machine is. So this only has one significant figure. So significant figures include all the digits that are needed to indicate the precision of a measurement or calculation. So I was saying it is useful for showing how precise your machine is that you're using in the lab. So for example here, we can look at, this is 8 milliliters of volume, and this is 9 milliliters of volume in a graduated cylinder. We have 8.1, 8.2, 8.3, 8.4, and then 8.5. So it's somewhere between 8.4 and 8.5 if you look at the meniscus here, which is going to come down a little bit like that. So we have to read to that bottom line. So it's somewhere, maybe it's 8.45, maybe it's a little bit higher, maybe it's 8.46. So this last number, we're not sure about. It's estimated. If I look at this example right here, I see 3 significant figures. I see an 8.45, maybe it's 8.46, maybe it's 8.47. Those are 3 significant figures. The hundredths digit is estimated. So here's the rules, and we'll be reviewing this a lot in class because it's really important. So any numbers that are just plain old numbers are significant. So all of these are significant, so the answer has 4 significant figures. This one has 3 because 1, 0, 4, zeros in the middle of numbers count. And so this has 3 significant figures. This one here, 2.600, because we have a decimal place and we see zeros at the end of a number, then those zeros are significant, so this has an answer of 4 significant figures. This one, however, is different because the zeros in the front don't count. They're just showing us how small this is. So I see a 560. This 0 counts because I see a decimal someplace in the number. So this has 3 significant figures. This one here, no decimal place, so I would say it has 1 significant figure. So we're going to do practice problems in class. There's rules for adding and subtracting these significant figures and then being able to round to an answer. So for example, if I have 2.50 and 2.5, when I add those together I get 5.00. Because this number is less accurate, this has 1 decimal place, one number after the decimal place, and this has 2. This machine is less accurate, so my answer has to be that way as well. So when we look at adding and subtracting, we round to the smallest number of decimal places. So in this example, it would be 1. So when we round, we're going to round to whatever we're asked to, and I'll tell you the rules about that. But say if I have to round this guy to 4 significant figures, I'm going to look at 1, 2, 3, 4. I'm going to look at that place. Then I'm going to look at the number after it. Is it a 5 or greater? No. So I'm going to answer, my answer as a rounded number would be 23.78. This doesn't go up. It stays the same because this is a 3, not a 5. Okay? But if they want me to change this to 3 significant figures, I'm going to go 1, 2, 3. Look at the number after it. Is it 5 or greater? Yes. So that means I have to make this guy go up by 1. So 12.2 is my answer for 3 significant figures. Multiplying and dividing have a different set of rules than adding and subtracting. So when we do this one, we look at how many sig figs we have here. We have 2 sig figs. Here we have 1. So our answer can only have 1. So we had to round this guy to 1 sig fig. Significant figures, I call them sig figs for short. This one here, I have 3 significant figures, 2 significant figures. My answer has to have 2. So that's how we do multiplying and dividing. It's a different rule than adding and subtracting. So we have to make sure we understand the difference between the 2 rules. This is something you need to work on a lot because we use it all semester long. And for some people, it's kind of a challenge to figure this out, how this works. We'll do lots of examples in class, but you'll probably have to do a lot on your own to get comfortable with it. So please spend some time on this. We're going to be doing something called scientific notation. And that's where we, instead of having to write all these zeros, we write things in an easier format for ourselves. So this is saying I have 6 zeros. This is saying I have 4 zeros. So it makes life a lot easier. We'll do a lot of practice problems with this in class. This one people forget, so please know this one here. 10 to the 0 power is always 1. So big guys have positive exponents, and little numbers, these are very, very small numbers, have negative exponents. Okay, so you have to know that rule. So please start thinking about that. So we can write things more easily for ourselves sometimes if we write them in scientific notation. So what we do is we have a number, a dot, and a number. So I'm going to move this decimal 2 times. Number, dot, number, number, dot, number. And then I said, hey, I moved it 2 times. That's for a big number. Remember, positive for big numbers. If I have a small number, I'm going to move the decimal 1, 2, 3. And since it's small, it's going to be a -3. I'm going to tell you, hey, it's a small number. I have a number, dot, number. And I'm saying it's a very small number. It's a negative exponent. So please start getting used to that. We'll do practice problems in class. So we're going to be converting from one thing to another, and we're going to be using something called dimensional analysis. And we'll need a conversion factor for it. You probably have done this many times when you make a recipe. You know that 3 teaspoons makes a tablespoon. That's a conversion factor. So we're going to change units often in class, and we need to change from one to another. We'll use something that we know, which is called a conversion factor. So these are conversion factors that you guys know already. So they're not hard. We're just going to use ones that you haven't used before, so that makes it a little more challenging. So you guys know that 3 feet is a yard. And you can flip conversion factors one way or the other depending on what you need in the problem. So we'll be practicing with these in things that you know, like time and distances, so you get used to doing dimensional analysis and using conversion factors. So this right here is an example of dimensional analysis. We start with what we know, and then we write a conversion factor to get to what we're trying to get to. So we're trying to cancel out the yards, and we're trying to get to feet. Okay? So we'll try these in class. We'll try those in class. So sometimes we have to go from English to metric, and so you'll have to use a particular conversion factor that we know from English to a metric unit, or from a metric unit to an English unit. And so we'll just have to know those conversions. I won't have you memorize a lot, but you'll have to know some. So we will be doing the lab in our first lab where we're going to be measuring things. So you'll get used to meters and decimeters and centimeters and things like that. So I'll help you with that in the lab. And some sample problems we'll do in class. Here's some more practice problems. And a little bit, some other things I need you guys to know are states of matter, and we're going to be talking about this a lot in class. You'll be using all these states of matter in labs and in your jobs as well, so I need you guys to understand the properties of all these. So solid, for example, you always know its shape and its volume. A liquid, you always know the volume, but it too can change its shape. And a gas, you don't know anything about it. It can change its volume and its shape. So those are the three states of matter. There's more states of matter that scientists have found out, but these are the things that we need to know for our working lives. And we're going to be talking about all different types of matter, and we can classify it. So matter overall can either be a mixture or it can be a pure substance. So for example, a cup of coffee is a mixture. It's got lots of different chemicals and water mixed together. A pure substance is the sugar that you put into your coffee. It's just plain old sugar, one molecule, that's it. These pure substances we can change. They can either be a compound, so sugar is a compound, or it can be an element. So sugar is made out of carbon, oxygen, and hydrogen. So if you do a chemical change, you can change your sugar into just carbon, hydrogen, and oxygen, separate it. You put them together, you can make sugar. Same thing with your coffee. You can do physical changes, like you can filter out the caffeine, or you can boil it off, and you can just get a pure substance, caffeine, or water. Here's examples of elements. These are elements you're going to see on the periodic table. And when you put elements together, they turn into compounds. So 2 H's and 1 oxygen, 2 hydrogens, 1 oxygen makes water. So elements are different than compounds. Compounds are made of elements. Another thing you might see in your jobs is working with density and specific gravity. So there's special things called hydrometers that you can put into a fluid. So sometimes they put urine in a particular container, and then they use one of these hydrometers to figure out the specific gravity of it. And that will tell you if the person's ill or not. So different things have different densities. Uranium is very dense. It's got a lot of mass for its size. Balsa wood is very light. You know, it floats on water, so it has very little matter for its size. Gases, look how small these are. They're very, very, very small. Very little matter for a particular volume of them. And we'll do density problems for math, and we'll need to know the mass, which is measured in grams, and we'll need to know the volume of the particular piece of material that we're looking at, and that will be measured in milliliters or cubic centimeters. And then we will just divide these, and so it's very, very easy math. You're just going to divide, and you'll find out the density in grams per mil. This is the unit for density. It's grams divided by mils. So you just take 7.453 in your calculator divided by 6.85, and you get that. And that's how you figure out a density of a material. So we'll do practice in class. Last little bit in this lecture is about energy. And energy is the capacity to cause change. One type of energy is kinetic energy, which is moving energy. Potential energy is stored energy. So all chemicals have elements bonded together, and when they do, they store energy in something called a chemical bond. We'll be doing energy calculations soon in class, and we'll be using these. These are conversion factors like we talked about before. So the food that you eat, we measure that in calories. Well, the calories you see on your food boxes are actually 1,000 small calories. So this is how we measure it in science, in the small c. The kind you see on the box of food is really a kilocalorie. We'll be using different temperature scales in this class. For example, we'll be doing Fahrenheit, Celsius, and degrees K, depending on the math that we're doing. So we just have to get used to that. So we're used to water freezing at 32, but if we're in the Celsius scale, we measure it and we say it's 0 degrees C. So it's good to know that water freezes at 0 degrees C and boils at 100 degrees C, because you'll need to know that in the laboratory when we're doing labs. So look on your thermometer, it's always going to be in C. So 0 is freezing and 100 is boiling. We'll also teach you guys how to do Fahrenheit to Celsius conversions. So we're going to use this formula. There's several formulas. They all do the same thing and they get you the right answer. So we'll find one that you guys feel comfortable with. But this is a good one right here. So you take if you want to go from Celsius to Fahrenheit, take your degrees C, multiply by 1.8, add 32. If you want to go from F to C, take the F number, subtract 32 from it, get that answer, and then divide in your calculator by 1.8. So we'll do practices in class. So that's it for this introductory lecture. I hope you listen to it before we meet in class, so you get used to this, and we'll talk about this and try to practice problems in class and in the HBA time that we have. Please email me if you have any questions, and please feel free to ask questions in class. It really helps all of us. If you have a question, generally a lot of other people have the question as well. So don't feel bad about asking questions. We really want it to be interactive so that I'm sure that I'm answering the questions and you guys feel comfortable in class. Alright, so I'll see you in the classroom. Thanks so much for listening and paying attention. I appreciate it. Have a great day.